like a ton of stuff I want to do for the review, and I only have like. Okay, so, today I need to teach you something here, this fancy, it's not, I promise you, it's no big deal. No, the words, you see theorem, you're like, "Oh, I'm not going to understand, except, no, it's not a big deal, I promise, just fancy words. And after today, I probably won't even say central limit theorem, we just call it CLT. No big deal. Okay, I promise, most of it is me running back and forth with the applet. So, I'm gonna be warm by the end of the period, running back and forth between you and my computer. Is the notes are just one page. Basically, the notes are Mrs. Talbot running back and forth. So we're actually, this is gonna be weird, but we're gonna start by showing you things with the applet, and we're gonna do this bullet point first. And then I'm gonna show you something else with the applet, and we're gonna do this bullet point. And then we're gonna combine those two pieces of information and use them to write the central limit theorem after. But I wanted that to be at the top of your notes, so that later when you're flipping back through, that would be something that would jump out at you. But anyway, so it's gonna go a little weird order, but most of it's just me, again, wearing a hole in the carpet back and forth between my desk and the thing. Okay, and interestingly enough, you do not need your yellow sheet today. There's no new formulas really. It's basically all about the shape of things. Okay, so I chose to use the CP/M applet instead of our books applet because our book did something stupid with it, which I can show you later if you're interested. But the CP/M one is saving. Okay. I wonder when they're gonna stop, like having this be public and just for people who have purchased CP/M ebook, and I'm just gonna hope that that never happens. Anyway. So, this is a normal-ish population, and I wouldn't expect that anything in real life would be perfectly normal. Right? If you have real data from, I mean, unless it's contrived like on your math problems. But if you're taking data from, let's just go with test scores here. So if you're taking data from test scores, it could be that you would have an average of 50. And it could be possible scores from 0 to 100. That would kind of make sense in this case. A lot of test scores are normally distributed. Not that I've graphed them or anything. Kind of sounds like maybe I have graphed them a little bit. But I overlaid the normal curve, so can you guys just, fuzz your eyes over and see that, it's following a normal shape. It's just not perfect because let's pretend it's real data. A little bit. Okay. All right, so what I'm interested in is not the shape of this. This is the shape of the real population. And if I had that information, I wouldn't actually need a sampling distribution. I could just look at the actual data, but let's pretend I don't have it. So I'm going to take out one sample. So over here, I have some things marked. I have one sample of size 2. Okay, so let's make sure that we understand what's happening here. Okay, so we took out 2 values from that population. The scale of this is very different, and you can't see it because it's teeny tiny. But this goes up to 1. This is saying it took one number from here, one number from here, averaged the 2 numbers, and plotted that here. Does that make sense? So sample of size 2, first number, second number, average of those 2 numbers. Okay. Only like the 3rd time too. Okay, I'm gonna hit it again. I'm not gonna do this like a million times. I just want to make sure you guys understand what's happening. Okay, so this is your new sample. It happened to be here and here. They averaged that and that right there. So that was the one from the last sample. This is the one from this sample. Does that make sense? You guys good so far? Okay, you understand what's happening. So if I go back there and hit the button a few times, you guys will understand what's going on, right? Okay, so. Okay. I have these two numbers were chosen, and the mean must have been this for the first one, and it must have been the same thing for the second one. New sample, new sample, new sample. Okay, everybody good so far? Now I'm gonna do the thing where I do like 500 of them at once. And what I want you to concentrate on is the shape down here on the third graph. Okay. What's the shape? Pretty normal. And what do you notice about the variability of it? The spread. Compared to the original. More compact, right? Less spread out because it's got a sample size of 2 instead of 1 for the original population. Okay, so that's where the standard deviation here is going to be whatever that was divided by square root of 2. And then divided by square root of whatever sample size is. Okay, so because you guys are looking at me like that, I'm just going to do a different sample size. Let's do a sample size of 10. Okay. What do you notice about the shape? Still pretty normal, right? What do you notice about the variability? Less, because you're going to go take the original divided by the square root of 10. Are you hanging with me? Okay, so as I increase sample size, that's a good thing. It decreases the variability. Okay, that was like past lessons. Today's lesson is about shape. So what do you notice about shape? Pretty normal. Okay, so would you feel confident for me saying that if the original population is normal, then the sampling distribution will also be normal? Okay, you feel like I've given you enough evidence to that fact? Okay, so that's the first bullet point we're going to fill in. Now, if any of you are someone who questions their teacher's teaching method, you know, one of those students is really critical of teachers, that student right now would be saying, this is Dava, shouldn't you have shown that to us yesterday? Isn't that really yesterday's lesson? Didn't you guys do all of your homework and calculations based on the fact that the population was normal, so you could assume that the sampling distribution was normal? Is it shocking though? No. Okay, what we really care about is how do I show the shape when it's not stated normal in a problem? So that's really what we're after. And so what I'm going to do is go back to the applet, give you something really weird.
Is that weird enough?
Mm.
Do you see the skew? She's pretty skewed. Weird enough for you? Okay, so we're gonna go with a sample size of 2. Just to start over my aerobics for the day. So it took out 2 things from that really skewed situation, and then it averaged them and plotted it here. Does it make sense that it would be kind of located over on this side probably? Most likely. Does it have to be? No. But the bulk of the data is over there. What predictions do you have? Do you think it's going to turn normal? Does it look like it's turning normal? No. Okay, now let me do the 500. Well, crap, it's skewed. Okay, so super right skewed graph. Population, I put it at, what did I do, 0.15, so way over on this side, on purpose, to try to make something extreme for you. Sample size of 2, and I got a skewed graph. Okay, now, I'm gonna show you some magic. Are you ready for magic? I don't know if you can handle the excitement of this. Oh, the pure excitement. So fascinating. Okay, here we go. It turned normal. Oh no. Ooh. Okay. And now I can go rest back there so I can. So the shape is all about sample size, and the golden number is 30. And that's why I put 30. So if your sample size is bigger than or equal to 30, then your sampling distribution will come out to be normal, and you can use normal CDF. That's the big central limit here. So all you have to do is look at the number of in your sample size and just state that it's greater than or equal to 30, and then you say, so CLT applies, and then you get to use normal. So that's basically your large counts condition for me, because there's no times P, right? Your brain is programmed to go n times P is greater than or equal to 10, but there's no P you plug in. So you got to use n. And what happens is basically the rule, the stats greater than or equal to 30. Now, let me show you the dumb thing about your book's applet. I don't understand. I really wanted to use it because, you purchase a textbook, you pay a lot of money for it. This is the applet for our textbook. I showed it to you before. What is the largest sample size they will allow me to show you? 25, but the rule is 30. Why would they do that? I don't understand this. They give you all of these stupid options. 16? Give me, you want me to show the children 16, but you didn't give me 30? And the whole thing is based around greater than or equal to. I don't know what kind of fool. I showed Miss Rice before school. She doesn't know anything about something up there. But she was like, I was just showing her how dumb it was. And she's like, are you going to send him an email? I was like, no. gonna complain in my YouTube video to get 7 views. So. It probably won't get any of those people. And they're just gonna be like, well, clearly, as the sample size increases, it's approaching normal, which is what they're gonna say. And I'm like, yeah, cool, but the industry standard is 30 and you gave me 25. Nice. Whatever. Okay. Okay, now I have to sort of eat my words in a minute here and say that there is one super cool thing about that applet. Okay, so here's my bullet point. I said, if the shape of the original population is not normal, then the shape of the sampling distribution will be normal if n is greater than or equal to 30. And then down here, what I want you to do, this is going to be like, let's just say that you're doing your homework and it says, what's the shape of the sampling distribution? You would say shape n equals 50. So you'd state what n is. 50 is greater than or equal to 30. So CLT applies. And that's how you're going to justify the shape like you would do n times p or n times 1 minus p. So this is what I want you to write. We still have to go back and say the central limit theorem, I realize, but I want to show you the one cool thing. Are there any of you that are questioning? I mean, I just showed you one example of a skew, and you're like, that's cool, Mrs. Talbot. It looked normal with a large sample size. Okay, but let me show you this. Look at how cool this app is. Okay, I have to say, I was really harsh about the one from your book, but look at this. I could make it anything I wanted it to be. I could just drag it over. This is online, by the way, if you want to play with it. Damien was playing with it the other day. Okay, so I made the weirdest bimodal goofy situation of all time. And I'm going to do 25 just to, I mean, that's the best I can do. Look at the sampling distribution. And I think that if the book was going to come here and send a representative by helicopter to definitely drop in with like some kind of ropes and explain themselves, they would say, well, 25 is pretty darn good, right? So I want you to take this wacky example that I made and show you that I'm not just making crap up here. It works for everything. You not to do weirdly bimodal, something that looks like the cliffs in Utah, you know, whatever. Now there is arts and crafts. I noticed that you noticed, but I did not define the central limit theorem yet. So grab your basket. That's fine. Hey, hold on, guys. I still have to fill in this whole giant gaping. Okay.
If you draw many samples of the same size from a population. Okay, can you guys picture this happening? Okay. And calculate the sample mean from each. Can you picture that happening? Okay, so there's the central limit there. It says, if you draw many samples of the same size from a population and calculate the sample mean for each, then the sampling distribution of the mean, meaning that sample mean, that's the symbol for sample mean, so you graph all the sample means, should be normal if n is greater than or equal to 30. The reason that I wrote large sample size in parentheses is because that's still large count. I want you to like trace that back to still being large count. It's just large count for means because you can't plug in n times c, there's no c to plug it. Okay, now arts and crafts. I must have been hanging out with my husband when I made this problem, but he is an automotive technician, I speak up. And he hates it when they give him oil changes because he's like a master diagnostic technician, and it's like really annoying that they would give him an oil change. Well, he still does, Ken. And he must have been complaining about it on the couch when I was writing my curriculum. Shocking. I love to hear his stories on the way home from work because crazy stuff happens at car dealerships. The other day, we were, so while you're arting and crafting and writing, I'll tell you two things. First, if you have a Tesla, every year Elon gives you a Christmas present. This year, our Christmas present is a month-long, like free self-drive, like full self-drive for free. Now, part of it, he wants you to experience it, so you'll buy it. Like, I know it's not just a present, it's a marketing gimmick. However, we have been playing with the full self-drive for, I think, we've had a Tesla since like 2020. And it has scared the bejesus out of us like 392 times, like so much that, you just gotta take the wheel, like it's bad. But, we go on 37 and I go on that scary thing where you go like down to Auto Mall Parkway and the cars are like coming off the 80. And I have to tell you, the latest version of the free self-drive has been perfect. I don't know what they did to fix it, but it's been beautiful. Anyway, the reason I'm telling you that is because we set it the other day for us to go to work. And so he put in Toyota Bleo, which is where he works. And we were like, I wonder what it's gonna do when it gets there, because it's like, it takes you to Toyota Vallejo, but like, where is it gonna park? Like, I don't know if you guys have ever been to Toyota Vallejo, but it's huge, and there's like multiple parking lots, and I was just like curious where it's gonna take us. So, you go in, like, up the ramp, in between the Mazda dealer and the Toyota dealer, and you go down the ramp with the Toyota Vallejo, and it goes around the back, and then, like, the back parking lot. And back there, there's one of those car carrier trucks. It's like foreshadowing of life. So there's one of those car carrier trucks that's bringing like new cars. By the way, weirdly enough, Brock Purdy bought like 12 brand new Toyotas. And it must be Christmas presents. He buys all of them through Toyota Vallejo. And anyway, so I know he was there like 3 weeks ago following my so anyway, so we get there and there's like all this brand new, beautiful, like 49ers, like the Sequoia, the really nice Sequoias anyway on this truck. And we're like, that's cool, whatever. And I'm like, worried about how the full self-drive's gonna handle basically anything. So it does really well and it pulls in the parks, whatever. I leave, I don't think about it. My husband texts me like 2 hours later and he goes, that like carrier thing? No, the guy, and he was like, it plowed into one of our employee cars when it was leaving and it pulled the whole like front of it off. Oh. These are the excellent stories I get to hear about Toyota Vallejo every day. Great. The dude's car is still sitting there. The front of it is just torn up. It's like laying in and the guy the truck is so big, the guy had no idea he even hit it. But it's on camera. There's your fun story for the day. I don't even know. I know. Can you imagine? Do you think that guy's fired? Anyway. Okay. I really only need another minute or two of your time here. So the time in minutes it takes an adorable, extremely tall, very particular technician to complete an oil change follows a right skew distribution with a mean of 30 minutes, a standard deviation of 20. He'd probably be angry with me that those numbers were so high. 40 customers are randomly selected. Calculate the probability that the average time it takes to complete the 40 oil changes exceeds 35 minutes each. Okay, to calculate the probability, just like you guys have been doing in all your homework this week, you've got to find shape, center, spread, and then hopefully normal CDF. That's the goal. Does that make sense to you guys? I hope so, after those last couple homeworks. Okay, so this shape. I really want to do N times P, but there's no P. So I remember, okay, Mrs. Talbot taught me central limit theorem. And that says that I have to find the sample size. The sample size is 40 in this problem because it says 40 customers are randomly selected. So I say N equals 40. 40 is greater than or equal to 30. So CLT applies. Check. So that's like your large counts condition for means. Okay, the center. The mean of the sampling distribution should be equal to the mean of the population. What's the population mean? 30 minutes. Okay, spread. I didn't leave myself a whole lot of room here. I'm gonna have to find the 10% condition and calculate the spread in this bit. Okay, so N equals 40. It's less than 10% of all, what was it? 40 what customers? Do you think that there could be more than 400 customers? I hope so. Okay, standard deviation of the sampling distribution is the standard deviation over the square root of N. What was the original? 20 over the square root of 40, which is 3.162. Oh, I don't know if I'm going to be able to fit this normal CDF right here. I'm just I'm just gonna have to. Wow. Okay. Hmm. Okay, greater than 35. What do I do? 35, infinity, really squishing this together. Mean, standard deviation. Look, I did it. Um, do I need to label anything? No, because the random variable notation takes care of the first two. Means labeled here, standard deviations labeled there. Are you guys okay if I just give you the answer? Okay, then write down this last bit. Does anybody know what to do for this question? This is a critical thinking, critical thinking, Mrs. Talbot, no. This is a critical thinking question. Oh, can I pause and say one more thing real quick? When you say so CLT applies, that means that you're saying it's normal. You don't have to state normal. I know that you mean it's normal if you say CLT. CLT is all about being normal. Okay, anyway, last thing. What is this answer? What kind of thing is this? Probability. This is a probability. Okay, what kind of thing is this? A probability. Okay, if I'm given a probability, how do I go backwards with normal stuff? Inverse norm. This is an inverse norm question. Okay, so we're going to write it out like the way that I'm hoping that your brain might think of it. So what I'm thinking is it should say the probability that X is less than or equal to some amount of time. Somebody's phone is dying or something. So I'm looking for this value equals 0.99. So how much time should they budget if they want to make sure that they gave him enough time? So it should be less than or equal to some amount. Reminding you that inverse norm is, I don't know, is already less than or equal to, but we're going to put the left in there just to remind you. It might be mine. Maybe something happened. Maybe the charger didn't charge. I don't know. But find inverse norm. It's right by normal CDF. Let's remind ourselves how to do that. What does it look for? So it wants the area, which is 0.99 in this problem. Okay. What's the mean in this problem? 30. Standard deviation. Okay, and then make sure that you are selecting the left tail because this is less than or equal to. If you have an older calculator, it's already defaulting for left, so you do not need to do anything. But I would need to give him 37.3 minutes, which believe you me, that place definitely counts it down to the portion of minutes that they will give them to do something. Which is kind of insane, but anyway. I must have been heated when I made this question. Or he was. I don't know. Something happened. Some kind of story. I'll have to ask him tonight on the way home, unless he has another juicy story for me. I'll have to listen to that. I do have a joke for you. It says, keep your eye on that guy, Tom. He's not, normal. I'm pretty sure that that's me, the bimodal guy there. Yeah. I think I should be that for Halloween next year. Yeah. Just some like wackily skewed graph. I don't know.